Angular acceleration. This angular acceleration, it is defined in a similar way like we define for the linear acceleration. That is, when a body moves along a straight line, the accelerations of the body is defined as what? The rate of change of linear velocity. So similarly, for angular acceleration, we define it as the rate of change of angular velocity. Fine. And this angular acceleration is denoted by alpha. Okay. Now, the average value, the average angular acceleration is given as alpha bar. And this is equals to the rate of change of angular velocity. If the angular velocity is omega, then rate of change of angular velocity means delta omega upon delta t. So this is the average angular acceleration. Now, like in case of linear accelerations, we have two values. One is average, and another is instantaneous. So therefore, in a similar way, we can define the instantaneous angular acceleration as alpha equal limit delta t tends to 0, because whenever the limit delta t tends to 0, then we get the instantaneous acceleration, or we can say this alpha is equals to, and instead of this we can write d omega upon dt. So this is the instantaneous angular acceleration. Now, this angular acceleration has a unit, and the SI unit of alpha, which means angular acceleration, it is equals to uh, radian. Okay, because we have seen before that this omega has a velocity, has a unit how much? Radian per second. So along with this second, it becomes radian per second square. Okay, and the dimension, of this angular velocity, it will be m naught l naught t minus 2. Okay, a relation between linear acceleration, that is small a, and angular acceleration, that is alpha. Okay, so we have seen before the relations between the linear velocity and the angular velocity, which is given as v equal omega r. Right? Now, if we differentiate this equation both sides with respect to time, so differentiating both sides with respect to time, let's say t, then you will get d dt of v, and right hand side d dt of omega r. Okay, or we can say this is dv upon dt. Now dv upon dt is what? The rate of change of v is what? V is linear velocity. So the rate of change of linear velocity is known as linear acceleration. So that is a. And we take this omega, this r outside the differentiation, and we differentiate only this omega. Then you will get a is equals to r. But again, this d omega upon dt, which is the rate of change of angular velocity, is equals to alpha. So this is the relation between linear acceleration and angular acceleration.